Hey everybody, welcome to this video on solving systems of equations. This is another one of those topics that you learned last year in Algebra 1, but we're going to do a refresher video for those of us who need it. A system of equations is two or more equations that have common variables. So something that might look like this: 3x plus 5y equals 17, x equals 5y minus 8. Or maybe something like this: 8x plus 2y equals 12, 7x minus 2y equals 30. Just made up some equations there. Two or more equations that have common variables. They don't have to be x and y. Maybe it's 4a is equal to 2b plus 6 and a minus 3b is equal to 12. So x and y, a and b, any two variables that are the same in both of the equations. The solution to a system of equations is an ordered pair, or a value for each of the variables that makes both of the equations true. So if you have this system, let's say here, 3x plus 5y equals 17 and x equals 5y minus 8, I haven't solved that system yet. When we look into solving a system like that, the answer that we get for x, and we'll get an answer for y, that is the pair of numbers that makes both equations true. To check that your solution to a system of equations is correct, you can plug your solution into both equations, and if the ordered pair, or the x and y value, or whatever the variables are, if those values make both of the equations true, then it is in fact the solution to the system of equations. And I'll go through that process of checking your solution when we get to some examples. A system of two linear equations can have 0, 1, or infinitely many solutions. There are three ways to solve a system of equations. We can solve a system of equations by graphing, by elimination, or by substitution. And so I'll talk about one, none, and infinitely many solutions as we get into some examples. But the three ways to solve a system of equations are going to be something that we really need to think about each time we solve a system, because we want to make sure that we are using the most effective method to solve a system of equations. So the first method of solving a system of equations is graphing. So that process, we would graph each line on the same coordinate plane, and the solution to the system is the point of intersection. So if we have a system of equations that when graphed, the lines look like this, let's say. So we have, let's say, one line here and another line here. The point where those two lines intersect, that is the solution to the system of equations. If two lines are parallel, meaning they never intersect, that system of equations has no solution. And if the two lines are the same line when graphed, so one line looks like that and the other line is the same line, there are infinitely many solutions to that system of equations. Every point on this line is a solution to the system. While it is important to be able to solve a system of equations by graphing, that often is not the most efficient method to solve a system of equations. So we're really going to focus on solving systems of equations by substitution or elimination. Those are both of the algebraic methods to solve a system of equations, okay? So substitution, thinking about the word substitute, that is when one of the equations is solved for one of the variables, and then you substitute that expression into the other equation. Okay, and then we'll have an equation with only one variable. We'll solve for that one variable, and then we'll plug this solution back in to solve for the other variable. So if you look at this first system example that I wrote up here, this is set up perfectly for substitution. Okay, this second equation tells me that x is equal to 5y minus 8. Okay, so what I would do is I would take this 5y minus 8 and substitute it directly here for x, and then I'll have an equation that only has y's in it. Then once I solve for y, I can use that value plugged into either of the equations to solve for x. The other algebraic method for solving systems of equations is elimination. Okay, elimination, if you think about the word elimination, the root of that is eliminate. Some teachers might refer to this method as the stack and add or stack and subtract method. But what our goal is that we want both of the equations to have a variable to have the same coefficient in both equations. So in this example that I had listed earlier, notice in the first equation we have 2y, in the second equation we have negative 2y. Those are the coefficients on the variable, the number in front of the variable. So the coefficients on y are 2 in the first equation and negative 2 in the second equation. If I simply add these two equations, 2y and negative 2y, those are going to eliminate. Okay, so elimination, we are just eliminating one of the variables when we either add or subtract the two equations once one of the variables in both equations has the same coefficient. If they have the same coefficient with opposite signs, like positive 2y and negative 2y, those cancel or eliminate when we add the equations. Okay, so we'd have here, if we added straight down, 15x is equal to 42, and then we would solve for x. If the two equations have the same coefficient for one of the variables, but they have also the same sign, we could subtract these two equations because 2y will cancel with 2y when we subtract. So we'd end up with 8x minus 7x is x. 2y minus 2y would cancel, and 12 minus 30 is negative 18. So we'd have x equals negative 18. So you also could, if you wanted to, you could have multiplied one of these equations by a negative 1, and then you would have added the two equations in order to eliminate the y's. So you might have to multiply one or both of the equations by a constant, a number, so that you can get one of the variables to have coefficients that are the same. Okay, and you'll see examples of that when we get into the examples. We talked about how you can determine whether a system of equations has no solution or infinitely many solutions from a graph. Algebraically, whether you're using elimination or substitution, if both variables cancel and the resulting equation is not true, something like 5 equals 0, then there is no solution. Alternatively, if both variables cancel and the resulting equation is always true, something like 0 equals 0 or 5 equals 5, then there are infinitely many solutions to the system. Any point on the line would be a solution to the system of equations. Okay, now that we've recapped, we're going to do some examples. All right, so these first couple examples we're going to solve algebraically using either substitution or elimination, and I'm going to talk through why one method is better than the other based on what I see each system set up when I look at the problem. So this first system, I have y equals 2x plus 1 is the first equation, and 2y minus x equals 8 is the second equation. The first equation is telling me that y is equal to 2x plus 1. So I have an expression for what y equals. This is the type of equation that is perfect for substitution. Okay? If I know that y is equal to 2x plus 1, I'm going to substitute that for y in the second equation. Okay? So the second equation says 2y, which I know is 2x plus 1, minus x is equal to 8. Now I'm just going to solve this like a regular equation. There's only x's in the equation. I'm going to distribute the 2. So this becomes 4x plus 2 minus x is equal to 8. 4x minus x is 3x plus 2 is equal to 8. Subtract 2 from both sides. This leaves me with 3x is equal to 6. Dividing both sides by 3, x is equal to 2. Okay, so now that I know what x is equal to, I can plug that back into either of the original equations from the system. Okay, I'm actually just going to plug them into both equations to show you that regardless of which equation we use, we'll get the same value for y. Okay, so if I use the first equation, y is equal to 2x plus 1. So y is equal to 2, x is 2, so I'll plug that in for x there, plus 1. Y is equal to 4 plus 1, so y is equal to 5. If I follow that same process but instead use the second equation, 2y minus x is equal to 8, 2y minus x is 2 is equal to 8, add 2 to both sides, 2y is equal to 10, so y is equal to 5. Okay, so the solution to this system is that x equals 2, y equals 5. We can write that as a point 2, 5. Now, the great thing about solving a system of equations, when there is a solution, you can know for sure that your solution is correct by checking your answer. Okay, so the solution is that x equals 2 and y equals 5. If I plug those values into both of the equations from the system, and both equations are true, then I know my answer is correct. So the first equation was y equals 2x plus 1. So y is 5 and x is 2. 5 is equal to 4 plus 1. 4 plus 1 is 5, so 5 equals 5. That's true. I also have to make sure the solution is true in the second equation. 2y minus x is equal to 8. That's the second equation. Plugging in y is 5 minus x is 2 is equal to 8. 10 minus 2, is that equal to 8? In fact, it is. Okay, so we have just confirmed, assuming you do that check correctly, we've confirmed that our answer of x equals 2, y equals 5 is the solution to this system. Okay, looking at this next example, the first equation says 2x minus 3y equals negative 8, and the second equation says 3y plus 4x equals negative 16. Now, none of the variables are solved for. Neither of these equations say x equals something or y equals something. And if I actually tried to solve any of these equations for x or for y, I'd end up with an equation that has a fraction in it if I wanted to just try to solve by substitution, and that's not going to be efficient. Okay, so this system is set up best for elimination. The only thing I notice here is that this is x and y, and this is y and x. So I'm just going to rearrange those so that the x's and the y's are stacked. So the first equation, 2x minus 3y equals negative 8, I'll leave as is. And the second equation is 4x plus 3y equals negative 16. And when I look at that, actually, I see that this equation has a negative 3y and this equation has a positive 3y, and those actually cancel by addition. So if I add everything in this equation, 2x plus 4x is equal to 6x, negative 3y plus positive 3y is going to cancel, and negative 8 plus negative 16 is equal to negative 24. To solve this, we'll divide both sides by 6, and we get that x equals negative 4. Now, once we know what x equals, we can plug back into either of the equations to solve for y. I'll plug into the first one. 2x minus 3y is equal to negative 8. We know that x is negative 4, so 2 times negative 4 minus 3y is equal to negative 8. That's negative 8 minus 3y is equal to negative 8. If you add positive 8 to both sides, that cancels this negative 8. We'll have negative 3y equals 0. When you divide both sides by negative 3, we get y is equal to 0. Okay, so far we have x is equal to negative 4 and y is equal to 0. I'm going to check that. I want to make sure that I'm right. Okay, so I'm going to check that. My first equation said 2x minus 3y equals negative 8. 2x is negative 4 minus 3y is 0 is equal to negative 8. 2 times negative 4 is negative 8 minus 3 times 0, which is 0. Negative 8 minus 0 is in fact negative 8. So the first equation checks. The second equation said 3y plus 4x is equal to negative 16. Okay, so 3y, I forget what it was already, plus 4x is equal to negative 16. 3y is 0 plus 4x is negative 4 equals negative 16. 0 plus negative 16 is equal to negative 16, and that is in fact true. Okay, so my solution is x equals 4. Nope, that's a negative 4. Y equals 0, so negative 4 comma 0. All right, looking at this next example, the first equation says 2x plus 1/2 y minus 2 is equal to 4x plus y. So I have x's and y's on both sides of the equation, and there's also a fraction in there. Don't be afraid of that. The second equation says 6x minus 2y is equal to 15. So in this first equation, I'm going to subtract 2x from both sides, so that 2x on the left side of the equation is gone. This will leave me with 1/2 y minus 2 is equal to 2x plus y. Now, I know a lot of us don't love fractions, okay? So to get rid of that fraction, if we multiply everything in this equation by 2, that's going to get rid of the fraction, because if you multiply the fraction 1/2 by 2, you're left with just the coefficient of 1. So if you multiply everything, you distribute this 2 to everything in the equation, this will be y minus 4 is equal to 4x plus 2y. Okay, now we have this equation with no fractions. I'm going to subtract the y from both sides, and I have negative 4 equals 4x plus y. Now, this is kind of set up already for elimination, with the x and the y on one side of the equation and the number on the other side. But because the coefficient on y is 1, right, like the number in front of y is 1, it's just invisible. Anything times 1 is itself. You could, if you prefer substitution, you could easily say that this equation is equal to y. It can be rewritten as y equals negative 4 minus 4x. Okay, if you're trying to solve for this y on that side of the equation. And then if you wanted, you could substitute that into this other equation. Actually, you know what? I'm going to do that since I've already done that. And then I'll go through after and show how you would have solved by elimination instead. Okay, so sometimes elimination is more efficient than substitution. Sometimes substitution is a little more efficient than elimination, although you could always multiply an equation in elimination to get it to be easier to work with. But sometimes you could use substitution or elimination just as effectively, and one's not better than the other. Okay, so if I'm going to solve this, 6x minus 2y, which is negative 4 minus 4x, is equal to 15. Okay, and then if I distribute this negative 2, 6x plus 8, and negative 2 times a negative 4 is a positive, and then plus 8x is equal to 15. Adding this 6x and 8x, I have 14x plus 8 is equal to 15. If I sum both sides, I have 14x is equal to 7. And then dividing both sides by 14, you get that x is equal to 7 over 14, or 1/2. Okay, now once we have that, you're going to plug back into either of the original equations to solve for y. In this case, I really don't want to plug back into the first equation as it was originally written, because it had lots of expressions on both sides and it had that fraction of 1/2. And you always want to make sure that you're plugging into one of the original equations that were given to you in the problem, because what if you made a mistake somewhere along the way here, right? Like if you made a mistake in this part, then this expression for y being negative 4 minus 4x is wrong. Okay, so you want to plug back into an original equation when you are solving for the other variable. So 6x minus 2y is equal to 15. Okay, x is 1/2, so 6 times 1/2 minus 2y is equal to 15. 6 times 1/2 is just 3, half of 6 is another way to think about it if you want. Minus 2y is equal to 15. Subtract the 3 from both sides. Negative 2y is equal to 12. Divide both sides by negative 2, and you get that y is equal to 6. Okay, so your solution here is x is equal to 1/2, y is equal to 6. So that is the coordinate 1/2, 6. Okay, I did say I'd go back and solve this same system by elimination. So if I go back, I had 4x plus y is equal to negative 4. And then the equation that we were given is 6x minus 2y is equal to 15. Okay, so now if you notice here, the x's don't have the same coefficient, right? In the first equation, the coefficient is a 4. In the second equation, it's a 6. The y's don't have the same coefficient either. In the first equation, it's a 1. In the second equation, it's a negative 2. So at this point, I can't just add the equations or subtract the equations because neither of the variables will cancel. In this case, you're going to have to multiply one or both of the equations so that you get a variable in the first equation to have the same coefficient as that variable in the second equation, and vice versa. So if you wanted to eliminate the x's, you'd have to multiply both equations so that your x coefficients were the same. So perhaps you'd want to multiply the first equation by 3 and the second equation by 2, and that would give you a 12x in the first equation and a 12x in the second equation, and then when you subtract, both of the x's will cancel. I'm not going to do that. Instead, I'm only going to multiply the first equation by 2, because when I do that, the y's are going to cancel. Okay, so you're going to distribute the 2 to everything in here. Okay, a lot of people often forget to distribute that 2 to the number on the other side of the equation. Okay, so this will be 8x plus 2y is equal to negative 8. And then if we add these equations, because these coefficients are opposite, negative 2, positive 2, those are going to cancel by adding. We'll have 14x is equal to 7, which, look at that, that's what we had before. X is equal to 7/14, which is 1/2. Now, I'm not going to go through the process and solve for y, because we already did that. So I just wanted to show you that you're going to get the same answer when you solve by elimination, as long as you follow the process correctly. Okay, this last example that we're going to solve algebraically has a lot of cleaning up to do in both the first equation and the second equation. Okay, so like the first thing we're going to do is get the equation so that the x's are combined, the y's are combined, and it looks a lot cleaner. Okay, so in the first equation, we are distributing this negative 3 to both of those parentheses. That becomes negative 3x minus 6, and then we still have the minus 4y plus 6x is equal to 17. And at this point, I'm just going to combine some like terms. So negative 3x and positive 6x is 3x minus 4y, and then minus 6 is equal to 17. I'll just add the 6 to both sides so that I have the x's and y's on one side of the equation and the number on the other. Looking at the second equation, I'm going to distribute the negative 2 to both of those terms. That becomes 8 minus 2y plus 6, okay? A negative times a negative is a positive. This is a negative 2 times a negative 3. Okay, so don't forget that. Minus 5x minus 1 is equal to negative 8. Doing some combining of like terms, 8 plus 6 minus 1, I believe that's 13. Minus 2y minus 5x is equal to negative 8. I will now subtract 13 from both sides to get that to cancel on the left. Negative 2y minus 5x is equal to negative 21. All right, so now I have two equations that are much cleaner to solve. 3x minus 4y is equal to 23. And negative 2y minus 5x is equal to negative 21. So the way I wrote that didn't stack the variables correctly. Okay, I was just recopying what I had written above. So I'm going to switch the order of the variables in the second equation so that the x's and the y's are stacked correctly. negative 5x minus 2y equals negative 21. All right, so now looking at this, the x's aren't going to cancel as is, the y's aren't going to cancel as is. If you want to cancel the y's, you could multiply the second equation by 2, and then those negative 4y and negative 4y terms would cancel by subtraction. Because in the previous example I showed the option that you're just multiplying one of the equations by a number in order to get a variable to cancel when you add or subtract, I'm going to eliminate the x's just to show you the process for when you have to multiply both equations. So there's no number that I can multiply 3 by to get negative 5, and no number that I can multiply negative 5 by to get 3. So instead, I'm going to have to multiply both of these equations to get the lowest common multiple between those two numbers. I mean, you could get this to be, 30, because 3 goes into 30 and negative 5 goes into 30, but you want to try to get the lowest common multiple to keep the numbers as small as possible, okay? So to multiply the first equation, we're going to multiply by 5, because I'll then have a 15x, and I'm going to multiply the second equation by 3, because then I'll have a negative 15x, okay? So we're distributing to everything. So this becomes 15x minus 20y is equal to, I believe that's 115. And then we'll distribute the 3 here to all of these terms. Negative 15x minus 6y is equal to negative 63. All right, because the coefficient of 15 and negative 15 on the x's and one in each equation are opposite signs, those are going to cancel by addition. 15x plus negative 15x cancel. Negative 20y plus negative 6y is negative 26y, and 115 plus negative 63 is 52. Okay, you'll divide both sides by negative 26 to solve for y. I believe 26 goes into 52 2 times, so y is equal to negative 2. Once you solve for that, you're going to go back up to one of the original equations. I know it's, kind of a messy equation, but you're going to go back to one of the original equations and solve for x, okay? So negative 3 times x plus 2 minus 4, y is negative 2, plus 6x is equal to 17. Distributing negative 3x minus 6 plus 8 plus 6x is equal to 17. Combining some like terms, negative 3x plus 6, x is 3x, negative 6 plus 8 is positive 2 is equal to 17. Subtract 2 from both sides, 3x is equal to 15, x is equal to 5. So we have a solution of 5, negative 2. If you go back and check that in both equations, you will see that it does, in fact, make both equations true. All right, and this last example we're going to solve by graphing. So the first equation says y equals 2x minus 7. That is in slope-intercept form. So this is a y-intercept of 0, negative 7, and a slope of 2. So I will plot 0, negative 7. Rise 2, run 1, rise 2, run 1, rise 2, run 1, rise 2, run 1. Okay, just following that positive 2 slope, up to right 1, up to right 1. On the left here of the y-intercept, if you wanted to go down to left 1, you could do that. And then you do your best to connect the points. If you have a ruler or the side of a binder, that's great. I did not, but did the best I could. All right, the second equation is in point slope form. So this is the x coordinate of a point opposite of the sign, and this is the y coordinate of a point true to the sign. So if this is a negative 6, the x coordinate of the point is a positive 6, and the slope is 3. So I'm going to plot the point 6, 5. Oh, looks like that is the point of intersection. And then I'm just gonna keep plotting the points on the line just to make sure that, see what happens here. But rise 3, run 1, rise 3, run 1, same thing in the other direction, down 3, left 1, down 3, left 1, etc. And Doing the best I can here. Those lines are pretty close to each other. This is the point of intersection. So the solution to this equation is the 0.65. X equals 6, y equals 5. And so I know that point is on the second line because I just plotted it. Like that's the point that I saw algebraically from the equation. If I check this just by plugging into the first equation, 5 is equal to 2 times x, which is 6, minus 7. 5 is equal to 12 minus 7. 5 is in fact equal to 5. All right, so now it's time for you to do some practice problems on solving systems of equations. Thanks for watching. Have a good day.